All right, perfect. Thank you. And yeah, I really appreciate everybody coming out virtually today. I hope there can be some small amount of respite from the kind of seemingly endless, the tragedy of Ukraine, but also just the online and social media space being like a big part of both my concern and everybody else's concern. So maybe just take this time to spend a few minutes away from it, try and focus on these research questions. And yeah, hopefully, because it's quite a small group today, that we can have more of an intimate and interactive session. So we will take questions at the end, but of course, feel free to unmute and ask for clarification during the presentation as well. I hope it's interesting, and I hope that these are interesting research questions for you guys as well. So I'll just give a little bit of a background to myself and my involvement with the project that I'm going to talk around, and then we'll get into some of the kind of challenges around pollution prediction and using how we can use open geospatial software and different toolkits provided to us to analyze some of those research questions. Okay, so yeah, a bit about my background. Thanks for introducing me already. I am a data scientist at the UK's AI and Data Science Institute. That's the Alan Turing Institute. My role at the Turing is very broad. One day I can be researching 18th century maps and looking at proximity to railways in the Industrial Revolution. The next day I can be building kind of software web apps for high security research environments. But of course, I've also done work on air pollution prediction here. Most recently, my work involving Clean Air London and looking at building the technology stack and machine learning prediction algorithms for their real-time air pollution prediction network. And so I'm going to talk a little bit about work around air pollution prediction, but in a context of a different project. But that's a bit more about my background at the Turing. So what's the research challenge that I'm going to be discussing today? Well, it's primarily to do with air pollution, but not just only air pollution, about the exposure of child populations to air pollution. So we have actually, well, Unicef have actually done some research on this aggregate kind of statistic, and they've come across with 1 billion children, and that's actually 93% of the total child population below 15 years old as being exposed to air pollution. Now that's a large sum of children, and when we actually say, you know, how are they exposed and what type of pollution, well, we're actually talking about particulate matter. This is kind of small particulates that are suspended in the air. And we're concerned with the ones that are less than 2.5 micrograms. So a microgram is 1/1,000,000th of a gram. And we want, so the particles that are 2.5 micrograms, and we're concerned with the concentration of those within a cubic meter of air. So that's kind of how that's the metric of the pollution that we're looking at measuring. Now, the reason why we're concerned about this with children populations is because the impact of air pollution is felt more acutely by the young, and you can see on this slide that 1 out of every 10 child deaths under 5 years old is caused by pollution. The reason is because children have kind of small and very underdeveloped lungs, and this means that they can't filter out particulate matter in the same way that adult populations. And so they actually suffer a lot more acutely from respiratory infections. And this is why we see a large amount of child deaths being caused by respiratory illness. But of course, any level of high and continued exposure as a child, if it doesn't, unfortunately end in child mortality, can kind of propagate into older life and lead to respiratory complications then as well. So there's really a kind of unanimous concern around child population exposure to pollution because of this bifold effect. So we know that this is the problem, but we want to understand where the problem is. And how we understand where is by collecting information on pollution. And primarily this is done through ground sensors. Ground sensors are basically point location sensors. They're on the ground, and they capture the kind of real-time concentration of this particulate matter per cubic meter of air across. Granularity can be anything from minutes to an hourly concentration to a day average concentration. But as you can see, ground sensors are not enough. We don't have a ground sensor in every single meter of land on the planet, and therefore we can't kind of capture the understanding of what those concentrations are and where child populations are just using this source alone. And just to substantiate this point, here you can see a map of the locations of ground sensors. They're the kind of neon green points. And then the child population density is shown by this kind of raster image going from black, which is really, really low density of child population coverage, to bright yellow and almost to white in the kind of extremely highly dense child populations in the world. And we can see the distribution is not exactly the same. Some key areas on here to note are the area in the Rift Valley. That is, if I just show you with my cursor, that's this area here, just by the Horn of Africa, where we only really have 1 or 2 sensors to try to measure and establish the pollution concentrations for all of that high density child population area. And also we see the same occurring in the west of Africa as well. Now there are areas in this map, such as India, that have moderately dense PM2.5 sensor coverage. You can see there's a kind of cluster of bright green points across the Indian continent, but the actual fact that we have such a high population density covering the whole of India means that even with this moderate coverage, we are unable to use sensors alone to establish pollution measures and intersect those with the populations there as well. So we have a spatial coverage issue here. We also have a temporal data issue as well. Now this is now because of the COVID-19 situation, is that we can't actually use historic values to look and predict future values. Let me substantiate this again with a graph. So here you can see the seasonal PM2.5 concentration. So what that means is for every month, we calculated the average PM2.5 level captured in this micrograms metric again. And we averaged those globally, and we then looked at comparing 2019, so a year that was primarily pre-pandemic for most of the world, and then 2020, where we saw large lockdowns coming in around March time and lasting for most of the year, if not up until the summer months. So both years show completely different concentration behavior. And this shows that we can't use, for example, 2019 data to look and predict into the future for 2020. So we have both a spatial concentration issue of sensors and a temporal value and accuracy issue as well. So how do we deal with both of those? Well, imagine if we could monitor air pollution and predict exposure across regions where current data is inaccurate. And the way that we can do this is through machine learning. So this is a GIF. It's quite slow rendering, so you can see that we actually have on one side of the slide here, January 2020 predictions, and the other side we have July 2020 predictions. Now, if we cast our mind back, January 2020 was a month where we actually didn't really see the effects of the pandemic in at least the Western Europe or in Europe in general. But in July 2020, there were a large amount of places in Europe that had lockdown events happening. I'm just checking the questions. Oh, okay, it's just more. So we can actually see that from these predictions, there is a difference between the two. And those predictions are spatially distributed as well. Now, these are actually outputs from a machine learning model that myself and collaborators at Unicef worked on. So we are saying that basically, well, if we use machine learning techniques to be able to extrapolate both spatially and temporally, then we actually can get much better predictions of PM2.5 than if we were to just use sensor values alone. So how do we do this? Well, these are primarily the technologies that we use to develop our solution. What we mainly used as training data was OpenAQ. So OpenAQ is an open API. They're a provider, they're open source, and they provide hourly averaged pollution concentrations for most pollution sensors globally. Now you can extract a lot of different values from this. Obviously, in our case, we were focused on PM2.5, so that's that particulate matter at 2.5 micrograms. And we wanted to basically pull all of that information up until the point at which we saw deep lockdowns in the middle of 2020. And we were able to do that with that their open API. So that was really, really helpful. As well as this, we wanted to pull a large amount of information from satellite variables. So this kind of porthole window logo is Google Earth Engine, and we use Google Earth Engine to pull down useful satellite imagery such as AOD, that's aerosol optical density, a well-known proxy for PM2.5, which is captured at the weekly average level across the globe by open satellites from Google Earth. As well as this, we captured land use information from Copernicus satellites as well. And we were also provided with some other proprietary satellite information about the child population density and global population density as well, to give us a good indication of where population sensors were. For other land use information, we were using OpenStreetMap, another really valuable geospatial technology that has, again, an open API for pulling down location information from a crowdsourced platform called OpenStreetMap. And this helped us further identify land use and land formations that could be pollution sources. As well as this, we can talk briefly about the other technologies. We use Street View to validate some of the locations as well. Primarily, we were interested in school locations because of the exposure at schools for children populations. So we use that to validate. And we used it also to validate land use and pollution sources. The other technologies are tools such as the well-known library pandas and Postgres for hosting information, and Kepler GL for visualizing the output. So the GIF that you just saw previously was the output of our prediction algorithm hosted on a geospatial engine, and GitHub for remote collaboration. Cool, so what does this actually look like? Well, yes, we've talked about these APIs that were pretty pivotal for the technology itself. We were also able to partner with local and regional partners to get access to some more proprietary information on pollution sources and sensors that were not put onto OpenAPI, and also some population density statistics as well. The computational process I will go through in a minute, but that was done primarily in Python, looking at extracting that information for locations you're interested in, processing to standard format for machine learning, then modeling and validation and testing, which we'll go through, and then, of course, the visualization. So let me talk at a high level around our machine learning approach. Well, as we've said, that we know that both using only time series information and using only spatial information is not enough, but using both and combining a meta-learning algorithm in machine learning, which we'll talk about later, actually produced much more accurate results than each of those approaches individually. So the way that we did this was look at extracting information for the sensors, and we did that over time series. Then using those sensor locations to extract satellite observations. These are some of the satellites we were talking about earlier, AOD, land use, and population density. Combining those two sources and building a machine learning pipeline to be able to extract the relationships between the two. And then interpolating across space and validating the results using a test set. So that's at a high level, but let's look at it in some more detail. So the processing basically consisted of the two first steps, that is the data extraction, the PM2.5 extraction, and then the extraction of satellite imagery and various results from satellites based on the location of the sensors. So how did that work? Well, the input data that we have was the location information from the sensors themselves. What we then did here was we created a buffer around that point location. So we wanted to make sure we weren't just capturing the satellite data at that specific point, but something in the very, very local area, for example, in 75-meter buffer area. So we did that, and we aggregated that as well temporally at the weekly average rather than at the hourly area. As well as just capturing information at the point location of the sensor, we were interested in also capturing whether that sensor was in a city area or not. So for example, if you're in highly dense urban environments such as New Delhi, you might want to capture the fact that everywhere around you is also a highly dense urban environment. And this actually adds to the impact of a pollution in the location that you're in. Whereas if you're in a very rural environment, then that might be a different case. And also maybe if you're by a main road, so there is maybe high pollution where you are right on the road, but actually the road is surrounded by trees and fields, then actually you're not in a highly dense, concentrated, polluted environment. You're just by a feature that is highly polluting. And so that helped us kind of distinguish between those two areas. And the way that you extract this information at scale is very difficult when we are looking at predicting air pollution globally. Of course, extracting for both a point location and a whole city area over the whole world is very expensive. And we had to use another open source geospatial technology called GDAL to create a VRT file. So these are files that are highly compressed files that help you extract satellite information quickly and fast. So that's the process that we did, both the point and the city extraction for the satellite imagery. Then after we'd found those interesting locations and extracted both of those satellite variables at both of those geographic aggregations. We merged the set, and that was considered our feature data set, so a training data set that we would use to create a relationship with the ground truth data. That was the pollution concentration data we already had. This slide just illustrates that extraction process. So we take the 75-meter buffer around a point location. For example, want to extract AOD. This is what that would look like. But then also maybe this point is contained within a city. So we want to extract the city mask as well and capture that information at city level as well. So let's move on to the modeling now that we have the training data. Why do we want this approach? Well, our primary goal was to assist a decision maker. That is basically the way that we can decide what the correct pollution level is. And we wanted to make sure that we use models that provided more insight so we could actually derive relationships rather than using a black box technique. And this is because there's a trade-off between explainability and accuracy. So for us, working in collaboration with Unicef, we were very happy to trade off a little bit of accuracy for higher levels of explainability, because ultimately we wanted these pollution predictions to inform policy. So the modeling, well, I just explained the input data. This was the satellite measurements that we extracted. But the satellite data we used in general was AOD, so that's the proxy for PM2.5, NO2, which is another well-known pollutant, and population density and precipitation. So we use some other weather and meteorological variables that also confound measurements of pollution. For example, high precipitation actually reduces pollution, and as well as kind of wind speed and everything like this. Of course, the target was PM2.5, and the modeling approach we used was called a stacking regressor. So these are this is a type of meta learning technique where you have two levels of modeling. Level 0 is individual models. So in that context, we used something called XGBoost, Light GBM Random Forest, all decision tree based algorithms. And then the weightings from those algorithms, we then passed on to a higher level model, which was a kind of linear regression model, and where you actually learn the relationships between the weightings of those models. So this is called meta learning, and it's a way that we benefit from all of the different techniques explored by each of those models. We learn the relationships between those. And we found that this actually worked quite well because we had a lot of different variabilities coming up in a global model, much more than you would see in like a city-based model of pollution. So we could actually lean on, we could exploit a lot of good techniques from all of those within the meta-learning methods. We did that process of training 5 times, and we then had some proprietary results, such as median absolute error being 5.6. This was actually pretty good because we found that, the results were highly variable, as you can imagine, from very rural areas with very little pollution to extremely high pollution values. And we also saw that the RMSE was 22.8, so this is actually pretty good compared to other global pollution models. And the explainability is not so good, so we're only scoring 0.49 out of 1. So we found that explainability was challenging because of the variation, but we always knew that this would be a challenge because we were building a global model, and we would be able to improve on this if we were doing much smaller city-based models. This is just a diagram showing that training process, where we have the level 1 training algorithms and a meta-regressor to understand the relationship between the weights of those algorithms. And then this is what we use to test on and get the final prediction from the unseen pollution values. And to validate, of course, we used feature importance. So here we can see the features at the top, the ones that are coming out as highly scoring is average population density being a good predictor of where high pollution was, as well as other metrics like city AOD, city NO2, and NO2 itself. And then some visual mapping as well. Here we have a snapshot of the pollutions over Hanoi. So we're taking the open AQ sensor station just with one sensor here, which has a mean of 15. And our prediction is mean of 15 as well. So this was okay. And in contrast, here is a much more rural province in Vietnam where we're seeing kind of lower scores of 9 micrograms per cubic meter of air. And again, taking a random sample of 106 points, we then collected all the information from the weekly average satellite variables for each of those points. And then predicting on those, we managed to get a pretty good representation of concentration. And this is the model validation process. So we wanted to deliver results to Unicef because this was primarily a project for them to help understand the effects of lockdown, pre and post lockdown. And what we actually saw was some surprising conclusions. On the left here, we have populations exposed to over 25 parts per million. So this is considered by the World Health Organization as like an extremely high level of pollution that you could be exposed to. If you're exposed to PM 2.5 above this level for over 24 hours, the WHO say this is like damaging for your health. And we saw before lockdown, places like Vietnam had pretty high number of children exposed to this level, but with the reduction after lockdown. So this made quite a lot of sense. But we were also seeing some areas see very little change, like Colombia, and some areas see increase in PM 2.5 after lockdown. So this date is like the first week of July that we were taking here. Again, in Nigeria and Peru. So yeah, we were confused by this. We thought maybe this is a challenge because we have very little coverage of sensors in Nigeria and Peru, and we thought maybe that it would be difficult to represent the situation there with the fact that we have very limited training data. But there was also some evidence as well that a lot of pollution was being moved into more residential areas during lockdowns because work and people were staying closer to home. So this was also a theory as well. And then on the right, we have, we see most of the time a reduction or a continuation of the same level for child populations exposed to over 10 parts per million. So this is if you're exposed to this for a long time, then it's damaging, but it would have to be over a course of a year rather than a course of 24 hours. And again, the same with schools. We saw some increase and some similarity, but yeah, we were surprised to see that actually there was higher pollution around school areas within lockdowns as well. So wrapping up, we decided to adopt an open source approach to the code. So all of this is available online, and we would really like it if you forked or started a repository and took a look. A lot of the work that we have done is extendable in a way that doesn't have to be related to pollution. We took the approach of building a pipeline to extract whatever satellite imagery is interesting for whatever point location is interesting. And that doesn't necessarily have to be about pollution, but this was the use case in our case. And the next steps for us, well, we are still working with Unicef, and we are targeting country offices that have high population densities for children under 14 years old. This is a time when pollution can affect your health at the most severe. So we are looking at working further with the Peru and Brazil office, as well as India, Vietnam, and Myanmar to for them to adopt this approach to pollution modeling. It's not only just a health cost, there is a economic cost of this as well. So we feel like there's a lot of value to be made in looking at pollution modeling and targeting pollution interventions using sources of information like this. And of course, we are also looking at addressing some of these sustainability goals. So these, additional partners that we're working with. And of course, if any of you know anyone interested working in the space and have also connections, then please let me know. I would really love to get more people involved. And keep in touch with me on Twitter, last_Christina.